This photo shows branch lightning coming from a dark cloud and hitting the ground. Figure 4.1, you can use probability and discrete random variables to calculate the likelihood of lightning striking the ground 5 times during a half-hour thunderstorm. Credit, modification of work CG Lightning Strike by Axel Reuven/Flickr, CC by 2. Chapter Objectives. By the end of this chapter, the student should be able to recognize and understand discrete probability distribution functions in general. Calculate and interpret expected values. Recognize the binomial probability distribution and apply it appropriately. Recognize the Poisson probability distribution and apply it appropriately. Recognize the geometric probability distribution and apply it appropriately. Recognize the hypergeometric probability distribution and apply it appropriately. Classify discrete word problems by their distributions. A student takes a 10-question true-false quiz. Because the student had such a busy schedule, they could not study and guesses randomly at each answer. What is the probability of the student passing the test with at least a 70%? The manager of an auto dealership might be interested in the color preferences for new car buyers. Suppose on average the dealership sells 20 cars per month. What is the probability that a customer prefers red cars? These two examples illustrate two different types of probability problems involving discrete random variables. Recall that discrete data are data that you can count. A random variable describes the outcomes of a statistical experiment in words. The values of a random variable can vary with each repetition of an experiment. Random variable notation. Uppercase letters such as X or Y denote a random variable. Lowercase letters like X or Y denote the value of a random variable. If X is a random variable, then X is written in words and X is given as a number. For example, let X equals the number of heads you get when you toss 3 fair coins. The sample space for the toss of 3 fair coins is TTT, THH, HTH, HHT, HTT, THT, TTH, HHH. Then X equals 0, 1, 2, 3. X is in words and X is a number. Notice that for this example, the X values are countable outcomes. Because you can count the possible values that X can take on and the outcomes are random, the X values 0, 1, 2, 3, X is a discrete random variable. Collaborative exercise. Toss a coin 10 times and record the number of heads. After all members of the class have completed the experiment, tossed a coin 10 times and counted the number of heads, fill in table 4.1. Let X equals the number of heads in 10 tosses of the coin. X frequency of X relative frequency of X. Table 4.1. Which value S of X occurred most frequently? If you tossed the coin 1,000 times, what values could X take on? Which value S of X do you think would occur most frequently? What is the relative frequency column sum to? A discrete probability distribution function has two characteristics. Each probability is between 0 and 1 inclusive. The sum of the probabilities is 1. Example 4.1. A child psychologist is interested in the number of times a newborn baby's crying wakes its mother after midnight. For a random sample of 50 mothers, the following information was obtained. Let X equals the number of times per week a newborn baby's crying wakes its mother after midnight. For this example, X equals 0, 1, 2, 3, 4, 5. Px equals probability that X takes on a value X. XPX. Px equals 0 equals 250. 1px equals 1 equals 1150. 2px equals 2 equals 2350. 3px equals 3 equals 950. 4px equals 4 equals 450. 5px equals 5 equals 150. Table 4.2. X takes on the values 0, 1, 2, 3, 4, 5. This is a discrete PDF because each px is between 0 and 1 inclusive. The sum of the probabilities is 1, that is 250 plus 1,150 plus 2,350 plus 950 plus 450 plus 150 equals 1. Try it 4.1. A hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. Let X equals the number of times a patient rings the nurse during a 12-hour shift. For this exercise, X equals 0, 1, 2, 3, 4, 5. Px equals the probability that x takes on value x. Why is this a discrete probability distribution function? 2 reasons. Xpx. Px equals 0 equals 450. 1px equals 1 equals 850. 2px equals 2 equals 1650. 3px equals 3 equals 1450. 4px equals 4 equals 650. 5px equals 5 equals 250. Table 4.3. Example 4.2. Suppose Nancy has classes 3 days a week. She attends classes 3 days a week 80% of the time, 2 days 15% of the time, 1 day 4% of the time, and no days 1% of the time. Suppose 1 week is randomly selected. Problem. A. Let x equals the number of days Nancy. B. X takes on what values? C. Suppose 1 week is randomly chosen. Construct a probability distribution table called a PDF table like the one in example 4.1. The table should have 2 columns labeled X and PX. What does the PX column sum to? Solution. A. Let x equals the number of days Nancy attends class per week. B. 0, 1, 2, and 3. Say XPX 001, 1004, 2015, 3080. Table 4.4. Try it 4.2. Jeremiah has basketball practice 2 days a week. 90% of the time he attends both practices. 8% of the time he attends one practice. 2% of the time he does not attend either practice. What is X and what values does it take on? The expected value is often referred to as the long-term average or mean. This means that over the long term of doing an experiment over and over, you would expect this average. You toss a coin and record the result. What is the probability that the result is heads? If you flip a coin 2 times, does probability tell you that these flips will result in 1 heads and 1 tail? You might toss a fair coin 10 times and record 9 heads. As you learned in probability topics, probability does not describe the short-term results of an experiment. It gives information about what can be expected in the long term. To demonstrate this, Carl Pearson once tossed a fair coin 24,000 times. He recorded the results of each toss, obtaining heads 12,012 times. In his experiment, Pearson illustrated the law of large numbers. The law of large numbers states that, as the number of trials in a probability experiment increases, the difference between the theoretical probability of an event and the relative frequency approaches 0. The theoretical probability and the relative frequency get closer and closer together. When evaluating the long-term results of statistical experiments, we often want to know the average outcome. This long-term average is known as the mean or expected value of the experiment and is denoted by the Greek letter mu. In other words, after conducting many trials of an experiment, you would expect this average value. The mean mu of a discrete probability function is the expected value. Letter 1 D707 equals sum, letter 1 D465, letter 1 D443, letter 1 D465. The standard deviation, sigma, of the PDF is the square root of the variance. Letter 1 D70E equals sum, letter 1 D465, letter 1 D7072, letter 1 D6F2, letter 1 D465, square. When all outcomes in the probability distribution are equally likely, these formulas coincide with the mean and standard deviation of the set of possible outcomes. Note: to find the expected value or long-term average, mu, simply multiply each value of the random variable by its probability and add the products. Example 4.3. A soccer team plays soccer 0, 1, or 2 days a week. The probability that they play 0 days is 0.2, the probability that they play 1 day is 0.5, and the probability that they play 2 days is 0.3. Find the long-term average or expected value mu of the number of days per week the soccer team plays soccer. To do the problem, first let the random variable x equals the number of days the soccer team plays soccer per week. X takes on the values 0, 1, 2. Construct a PDF table adding a column x asterisk p, x. In this column, you will multiply each x value by its probability. xpx x asterisk px. 0020, 02 equals 0. 105105 equals 0.5. 203203 equals 0.6. Table 4.5 Expected Value Table. This table is called an expected value table. The table helps you calculate the expected value or long-term average. Add the last column x asterisk px to find the long-term average or expected value. 0, 0, 2 plus 1, 0, 5 plus 2, 0, 3 equals 0 plus 0.5 plus 0.6 equals 1.1. The expected value is 1.1. The soccer team would, on the average, expect to play soccer 1.1 days per week. The number 1.1 is the long-term average or expected value if the soccer team plays soccer week after week after week. We say mu equals 1.1. Try it 4.3. A customer orders 1, 2, or 3 bottles of water. The probability of ordering 1 bottle is 0.6, the probability of ordering 2 bottles is 0.3, and the probability of ordering 3 bottles is 0.1. Find the long-term average or expected value mu of the number of bottles a customer will order. Example 4.4. Find the expected value of the number of times a newborn baby's crying wakes its parents after midnight. The expected value is the expected number of times per week a newborn baby's crying wakes its parents after midnight. Calculate the standard deviation of the variable as well. xpx x asterisk px x mu 2 px. Px equals 0 equals 250. 0, 250. Equals 0, 2, 1, 2, 0.04 equals 0.1764. 1 px equals 1 equals 1150. 1, 1150. Equals 1150. 1, 2, 1, 2, 0.22 equals 0.2662. 2 px equals 2 equals 2350. 2, 2350. Equals 4650. 2, 2, 1, 2, 0.46 equals 0.0046. 3 px equals 3 equals 950. 3, 950. Equals 2750. 3, 2, 1, 2, 0.18 equals 0.1458. 4 px equals 4 equals 450. 4, 450. Equals 1650. 4, 2, 1, 2, 0.08 equals 0.2888. 5 px equals 5 equals 150. 5, 150. Equals 550. 52120.02 equals 0.1682. Table 4.6 You expect a newborn to wake its parents after midnight 2.1 times per week, on the average. Add the values in the third column of the table to find the expected value of x. Mu equals expected value equals 10,550. Equals 2.1. Use mu to complete the table. The fourth column of this table will provide the values you need to calculate the standard deviation. For each value x, multiply the square of its deviation by its probability. Each deviation has the format x mu. Add the values in the fourth column of the table. 0.1764 plus 0.2662 plus 0. 46 plus 0, 1458 plus 0, 2888 plus 0, 1682 equals 15. The standard deviation of x is the square root of this sum. Sigma equals 1. Approximately 1247. Try it 4. For a hospital researcher is interested in the number of times the average post-op patient will ring the nurse during a 12-hour shift. For a random sample of 50 patients, the following information was obtained. What is the expected value? Xp x 0p x equals 0 equals 451p x equals 1 equals 852p x equals 2 equals 1653p x equals 3 equals 1454p x equals 4 equals 655p x equals 5 equals 250. Table 4. 7. Example 4. 5. Suppose you play a game of chance in which 5 numbers are chosen from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A computer randomly selects 5 numbers from 0 to 9 with replacement. You pay $2 to play and could profit $100,000 if you match all 5 numbers in order. You get your $2 back plus $100,000. Over the long term, what is your expected profit of playing the game? To do this problem, set up an expected value table for the amount of money you can profit. let x equals the amount of money you profit. The values of x are not 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Since you are interested in your profit or loss, the values of x are $100,000 and -$2. To win, you must get all 5 numbers correct in order. The probability of choosing one correct number is 110 because there are 10 numbers. You may choose a number more than once. The probability of choosing all 5 numbers correctly and in order is 110, 110, 110, 110, 110 equals 1, 10 minus 5 equals 0. 1. Therefore, the probability of winning is 0, 1, and the probability of losing is 1 minus 0. 0, 0, 0, 0, 1 equals 0. 99,999. The expected value table is as follows: xp x x asterisk p x loss 2 0 99,999 2 0. 99,999 equals 199,998 profit 100,000 0 1 100,000 0 1 equals 1 table 4 8 alpha the last column 199,998 plus 1 equals 0 99,998 since 0 99,998 is about 1. You would, on average, expect to lose approximately $1 for each game you play. However, each time you play, you either lose $2 or profit $100,000. The $1 is the average or expected loss per game after playing this game over and over. Try it 4. 5. You are playing a game of chance in which 4 cards are drawn from a standard deck of 52 cards. You guess the suit of each card before it is drawn. The cards are replaced in the deck on each draw. You pay $1 to play. If you guess the right suit every time, you get your money back and $256. What is your expected profit of playing the game over the long term? Example 4. 6. Suppose you play a game with a biased coin. You play each game by tossing the coin once. P heads equals 23, and P tails equals 13. If you toss a head, you pay $6. If you toss a tail, you win $10. If you play this game many times, will you come out ahead? Problem A. Define a random variable x. B. Complete the following expected value table. X. Win 10, 13. Lose 123. Table 4.9. C. What is the expected value mu? Do you come out ahead? Solution. A. X equals amount of profit. B. XPX. Win 10, 13. 103. Lose 623. 123. Table 4.1. C. Add the last column of the table. The expected value mu equals 23. You lose on average about 67 cents each time you play the game, so you do not come out ahead. Try it 4.6. Suppose you play a game with a spinner. You play each game by spinning the spinner once. P red equals 25. P blue equals 25. And P green equals 15. If you land on reds, you pay $10. If you land on blue, you don't pay or win anything. If you land on green, you win $10. Complete the following expected value table. XPX. Red 205. Blue 25. Green 10. Table 4.11. Like data, probability distributions have standard deviations. To calculate the standard deviation, sigma, of a probability distribution, find each deviation from its expected value, square it, multiply it by its probability, add the products, and take the square root. To understand how to do the calculation, look at the table for the number of days per week a men's soccer team plays soccer. To find the standard deviation, add the entries in the column labeled x mu to px and take the square root. xpx asterisk px x mu to px. 002002 equals 011202 equals 0.242. 105105 equals 0. 51111205 equals 0.005. 203203 equals 0. 62111203 equals 0.243. Table 4.12. Add the last column in the table. 0.242 plus 0.005 plus 0.243 equals 0.49. The standard deviation is the square root of 0.49, or sigma equals 0.49 square. Equals 0.7. Generally, for probability distributions, we use a calculator or a computer to calculate mu and sigma to reduce round-off error. For some probability distributions, there are shortcut formulas for calculating mu and sigma. Example 4.7. Problem: toss a fair six-sided die twice. Let x equals the number of faces that show an even number. Construct a table like table 4.11 and calculate the mean mu and standard deviation sigma of x. Solution: tossing one fair six-sided die twice has the same sample space as tossing two fair six-sided dice. The sample space has 36 outcomes. 1 1 1 2 1 3 1 4 1 5 1 6 2 1 2 2 2 3 2 4 2 5 2 6 3 1 3 2 3 3 3 4 3 5 3 6 4 1 4 2 4 3 4 4 4 5 4 6 5 1 5 2 5 3 5 4 5 5 5 6 6 1 6 2 6 3 6 4 6 5 6 6. Table 4.13. Use the sample space to complete the following table. X mu 2. Px 0 936. 0 1 2 936. Equals 936. 1 1836. 1836. 1 1 2 1836. Equals 0. 2 936. 1836. 2 1 2 936. Equals 936. Table 4.14. Calculating mu and sigma. Add the values in the third column to find the expected value. Mu equals 3636. Equals 1. Use this value to complete the fourth column. Add the values in the fourth column and take the square root of the sum. Sigma equals 1836 square. Approximately 0.7071. Try it 4.7. Add the values in the third column to find the expected value. Letter 1 D707 equals 3636 equals 1. Use this value to complete the fourth column. Add the values in the fourth column and take the square root of the sum. Letter 1 D70 equals 1836 square, approximately 7071. Two stacks of cards are placed on a table. Each stack has cards number 1 to 8. One card from each stack is picked up. Let x equals number of cards showing an odd number. Construct a table like table 4.11 and calculate the mean, micro, and standard deviation sigma of x. Example 4.8. Problem: on May 11, 2013 at 9:30 p.m., the probability that moderate seismic activity 1 moderate earthquake would occur in the next 48 hours in Iran was about 21.42%. Suppose you make a bet that a moderate earthquake will occur in Iran during this period. If you win the bet, you win $50. If you lose the bet, you pay $20. Let x equals the amount of profit from a bet. P win equals P 1 moderate earthquake will occur equals 21.42%. P loss equals P 1 moderate earthquake will not occur equals 100%, 21.42%. If you bet many times, will you come out ahead? Explain your answer in a complete sentence using numbers. What is the standard deviation of x? Construct a table similar to table 4.12 and table 4.13 to help you answer these questions. Solution: xpx x mu 2 px. Win 50 0 2140 210 7150 5006 20 2142 equals 648.0964. Loss 20 0 7858 15 716 20 5006 20 7858 equals 176.6636. Table 4.15. Mean equals expected value equals 10.71 plus 15.716 equals 5.006. If you make this bet many times under the same conditions, your long-term outcome will be an average loss of $5.01 per bet. Standard deviation equals 648.0964 plus 176. 6,636 square approximately 28, 7,186. Try a 4.8. On May 11, 2013 at 9:30 p.m., the probability that moderate seismic activity, one moderate earthquake, would occur in the next 48 hours in Japan was about 1.08%. As an example 4.8, you bet that a moderate earthquake will occur in Japan during this period. If you win the bet, you win $100. If you lose the bet, you pay $10. Let x equals the amount of profit from a bet. Find the mean and standard deviation of x. Some of the more common discrete probability functions are binomial, geometric, hypergeometric, and Poisson. Most elementary courses do not cover the geometric, hypergeometric, and Poisson. Your instructor will let you know if they wish to cover these distributions. A probability distribution function is a pattern. You try to fit a probability problem into a pattern or distribution in order to perform the necessary calculations. These distributions are tools to make solving probability problems easier. Each distribution has its own special characteristics. Learning the characteristics enables you to distinguish among the different distributions. There are 3 characteristics of a binomial experiment. There are a fixed number of trials. Think of trials as repetitions of an experiment. The letter n denotes the number of trials. There are only 2 possible outcomes called success and failure for each trial. The letter P denotes the probability of a success on one trial, and Q denotes the probability of a failure on one trial. PQ equals 1. The n trials are independent and are repeated using identical conditions. Because the n trials are independent, the outcome of one trial does not help in predicting the outcome of another trial. Another way of saying this is that for each individual trial, the probability P of a success and probability Q of a failure remain the same. For example, randomly guessing at a true-false statistics question has only 2 outcomes. If a success is guessing correctly, then a failure is guessing incorrectly. Suppose Joe always guesses correctly on any statistics true-false question with probability P equals 0.6. Then Q equals 0.4. This means that for every true-false statistics question Joe answers, his probability of success P equals 0.6 and his probability of failure Q equals 0.4 remain the same. The outcomes of a binomial experiment fit a binomial probability distribution. The random variable x equals the number of successes obtained in the n independent trials. The mean, mu, and variance, sigma 2, for the binomial probability distribution are mu equals np and sigma 2 equals npq. The standard deviation, sigma, is then sigma equals letter 1d45b letter 1d45d letter 1d45e square. Any experiment that has characteristics 2 and 3 and where n equals 1 is called a Bernoulli trial, named after Jacob Bernoulli, who, in the late 1600s, studied them extensively. Binomial experiment takes place when the number of successes is counted in one or more Bernoulli trials. Example 4.9. At ABC College, the withdrawal rate from an elementary physics course is 30% for any given term. This implies that for any given term, 70% of the students stay in the class for the entire term. A success could be defined as an individual who withdrew. The random variable x equals the number of students who withdraw from the randomly selected elementary physics class. Try 4.9. The State Health Board is concerned about the amount of fruit available in school lunches. 48% of schools in the state offer fruit in their lunches every day. This implies that 52% do not. What would a success be in this case? Example 4.1. Suppose you play a game that you can only either win or lose. The probability that you win any game is 55% and the probability that you lose is 45%. Each game you play is independent. If you play the game 20 times, write the function that describes the probability that you win 15 of the 20 times. Here, if you define x as the number of wins, then x takes on the values 0, 1, 2, 3, 20. The probability of a success is p equals 0.55. The probability of a failure is q equals 0.45. The number of trials is n equals 20. The probability question can be stated mathematically as p x equals 15. Try 4.1. A trainer is teaching a rescued dolphin to catch live fish before returning it to the wild. The probability that the dolphin successfully catches a fish is 35%, and the probability that the dolphin does not successfully catch the fish is 65%. Out of 20 attempts, you want to find the probability that the dolphin succeeds 12 times. State the probability question mathematically. Example 4.11. Problem. A coin has been altered to weight the outcome from 0.5 to 0.25 and flipped 5 times. Each flip is independent. What is the probability of getting more than 3 heads? Let x equals the number of heads in 5 flips of the fair coin. X takes on the values 0, 1, 2, 3, 4, 5. Since the coin is altered to result in p equals 0.25, q is 0.75. The number of trials is n equals 5. State the probability question mathematically. First, develop fully the probability density function and graph the probability density function. With the fully developed probability density function, we can simply read the solution to the question letter 1 D443, letter 1 D4653. Heads, letter 1 D443, letter 1 D4653 equals letter 1 D443, letter 1 D465 equals 4, plus letter 1 D443, letter 1 D465 equals 5 equals 0, 0146 plus 0, 0007 equals 0, 0153. We have added the 2 individual probabilities because of the addition rule from probability topics. Figure 4.2 also allows us to see the link between the probability density function and probability in area. We also see in Figure 4.2 the skew of the binomial distribution when p is not equal to 0.5. In Figure 4.2, the distribution is skewed right as a result of letter 1 D7 0, 7 equals letter 1 D45b, letter 1 D45d equals 1, 25. Because letter 1 D45d equals 0, 25. Histogram of probability density function of the given data. Figure 4.2. Letter 1 D443, letter 1 D465 equals letter 1 D4650 mu equals. Letter 1 D45b, letter 1 D465, letter 1 D45d, letter 1 D465, 1 minus letter 1 D45d, letter 1 D45b minus letter 1 D465, 5 letter 1 D4650, 25 letter 1 D4650, 755 minus letter 1 D4650, etc. and p equals 1, 25. Try it 4.11. A fair 6-sided die is rolled 10 times. Each roll is independent. You want to find the probability of rolling a 1 more than 3 times. State the probability question mathematically. Example 4.12. Approximately 70% of statistics students do their homework in time for it to be collected and graded. Each student does homework independently. In a statistics class of 50 students, what is the probability that at least 40 will do their homework on time? Students are selected randomly. Problem A. This is a binomial problem because there is only a success there are a fixed number of trials and the probability of a success is 0.7 for each trial. B. If we are interested in the number of students who do their homework on time, then how do we define x? C. What values does x take on? D. What is a failure in words? E. If p plus q equals 1, then what is q? F. The words at least translate as what kind of inequality for the probability question p, x 40. Solution. A failure. B. X equals the number of statistics students who do their homework on time. C. 0, 1, 2, 50. D. Failure is defined as a student who does not complete their homework on time. The probability of a success is p equals 0.7. The number of trials is n equals 50. EQ equals 0.3. F greater than or equal to greater or equal to. The probability question is p, x greater or equal to 40. Try it 4.12. 65% of people pass the state driver's exam on the first try. A group of 50 individuals who have taken the driver's exam is randomly selected. Give 2 reasons why this is a binomial problem. Notation for the binomial. B equals binomial probability distribution function. XBNP. Read this as x is a random variable with a binomial distribution. The parameters are n and p. N equals number of trials. P equals probability of a success on each trial. Example 4.13. It has been stated that about 41% of adult workers have a high school diploma but do not pursue any further education. If 20 adult workers are randomly selected, find the probability that at most 12 of them have a high school diploma but do not pursue any further education. How many adult workers do you expect to have a high school diploma but do not pursue any further education? Let x equals the number of workers who have a high school diploma but do not pursue any further education. X takes on the values 0, 1, 2, 20 where n equals 20, p equals 0.41, and q equals 1, 0.41 equals 0.59, x b 20, 0.41. Find p x less or equal to 12, p x less or equal to 12 equals 0.9738, calculator or computer. Using the T83, 83 plus 84, 84 plus calculator. Go into second DISDR. The syntax for the instructions are as follows. To calculate x equals value, binompf n p number. If number is left out, the result is the binomial probability table. To calculate p x less or equal to value, binompf n p number. If number is left out, the result is the cumulative binomial probability table. For this problem, after you are in second DISDR, arrow down to binompf. Press enter. Enter 200.4112. The result is p x less or equal to 12 equals 0.9738. Note: if you want to find p x equals 12, use the PDF binompf. If you want to find p x 12, use 1 binompf 20 0 41 12. The probability that at most 12 workers have a high school diploma but do not pursue any further education is 0.9738. The graph of xb 20 0.41 is as follows. This histogram shows a binomial probability distribution. It is made up of bars that are fairly normally distributed. The x-axis shows values from 0 to 20. The y-axis shows values from 0 to 0.2 in increments of 0.05. Figure 4.3. The y-axis contains the probability of x, where x equals the number of workers who have only a high school diploma. The number of adult workers that you expect to have a high school diploma but not pursue any further education is the mean. Mu equals np equals 20, 0, 41 equals 8.2. The formula for the variance is sigma 2 equals n pi q. The standard deviation is sigma letter 1d45b letter 1d45d letter 1d45e square. Sigma equals 20, 0, 41, 0, 59 square. Equals 2.2. Try it 4.13. About 32% of students participate in a community volunteer program outside of school. If 30 students are selected at random, find the probability that at most 14 of them participate in a community volunteer program outside of school. Use the T83 plus or T84 calculator to find the answer. Example 4.14. Problem. In the 2013 Jerry's Artorama Art Supplies catalog, there are 560 pages. 8 of the pages feature signature artists. Suppose we randomly sample 100 pages. Let x equals the number of pages that feature signature artists. What values does x take on? What is the probability distribution? Find the following. Probabilities. The probability that 2 pages feature signature artists. The probability that at most 6 pages feature signature artists. The probability that more than 3 pages feature signature artists. Using the formulas, calculate the I mean and Roman 2 standard deviation. Solution. X equals 0, 1, 2, 3, 4, 5, 6, 7, 8. XB 1,008,560. Px equals 2 equals binompf 10,085,602. Equals 0.2466. Px less or equal to 6 equals binompf 10,085,606. Equals 0.9994. Px3 equals 1, px less or equal to 3 equals 1, binompf 10,085,603. Equals 1, 0.9443 equals 0.0557. Mean equals NP equals 100,8560. Equals 800,560. Approximately 1.4286. Standard deviation equals letter 1d45b letter 1d45d letter 1d45e square. Equals 108,560, 552,560 square. Approximately 1.1867. Try it 4.14. According to a Gallup poll, 60% of American adults prefer saving over spending. Let X equals the number of American adults out of a random sample of 50 who prefer saving to spending. What is the probability distribution for X? Use your calculator to find the following probabilities. The probability that 25 adults in the sample prefer saving over spending. The probability that at most 20 adults prefer saving. The probability that more than 30 adults prefer saving. Using the formulas, calculate the I mean and Roman 2 standard deviation of X. Example 4.15. The lifetime risk of developing cancer is about 1 in 67, 1.5%. Suppose we randomly sample 200 people. Let X equals the number of people who will develop cancer. Problem: what is the probability distribution for X? Using the formulas, calculate the I mean and Roman 2 standard deviation of X. Use your calculator to find the probability that at most 8 people develop cancer. Is it more likely that 5 or 6 people will develop cancer? Justify your answer numerically. Solution: X letter 1 D435 200 0 0 15. Mean equals letter 1 D45 B letter 1 D45 D equals 200 0 0 15 equals 3. Standard deviation equals letter 1 D45 B letter 1 D45 D letter 1 D45 E square equals 200 0 0 15 0 985 square equals 1 719 equals 0 9965. The probability that 5 people develop cancer is 0.1011. The probability that 6 people develop cancer is 0.05. Try it 4.15. During a certain NBA season, a player for the Los Angeles Clippers had the highest field goal completion rate in the league. This player scored with 61.3% of his shots. Suppose you choose a random sample of 80 shots made by this player during the season. Let X equals the number of shots that scored points. What is the probability distribution for X? Using the formulas, calculate the I mean and Roman 2 standard deviation of X. Use your calculator to find the probability that this player scored with 60 of these shots. Find the probability that this player scored with more than 50 of these shots. Example 4.16. The following example illustrates a problem that is not binomial. It violates the condition of independence. ABC College has a student advisory committee made up of 10 staff members and 6 students. The committee wishes to choose a chairperson and a recorder. What is the probability that the chairperson and recorder are both students? The names of all committee members are put into a box, and 2 names are drawn without replacement. The first name drawn determines the chairperson and the second name the recorder. There are 2 trials. However, the trials are not independent because the outcome of the first trial affects the outcome of the second trial. The probability of a student on the first draw is 616. The probability of a student on the second draw is 515. When the first draw selects a student, the probability is 615. When the first draw selects a staff member, the probability of drawing a student's name changes for each of the trials and therefore violates the condition of independence. Try it 4.16. A lacrosse team is selecting a captain. The names of all the seniors are put into a hat and the first 3 that are drawn will be the captains. The names are not replaced once they are drawn. One person cannot be 2 captains. You want to see if the captains all play the same position. State whether this is binomial or not and state why. There are 4 main characteristics of a geometric experiment. A trial is repeated until a success occurs. Think of this as 1 or more Bernoulli trials with all failures except the last one, which is a success. In other words, you keep repeating what you're doing until the first success. Then you stop. For example, you throw a dart at a bullseye until you hit the bullseye. The first time you hit the bull's is a success, so you stop throwing the dart. It might take 6 tries until you hit the bull. You can think of the trials as failure, 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 success, stop. In theory, the number of trials could go on forever. The repeated trials are independent of each other. The probability P of a success and the probability Q of a failure is the same for each trial. P plus Q equals 1. And letter 1 D45E equals 1 minus letter 1 D45D. For example, the probability of rolling a 3 when you throw 1 fair die is 1/6. This is true no matter how many times you roll the die. Suppose you want to know the probability of getting the first 3 on the 5th roll. On rolls 1 through 4, you do not get a face with a 3. The probability for each of the rolls is letter 1d45e equals 5/6. The probability of a failure, the probability of getting a first 3 on the fifth roll is 5/6, 5/6, 5/6, 5/6, 1/6 equals 0.0804. The random variable x represents the number of the trial in which the first success occurs. That is, x equals the number of independent trials until the first success. The following are additional attributes of the geometric distribution. The random variable is discrete. The random variable may be defined in two ways depending upon the analyst's interest. In the example above for throwing a die, the question was what is the probability that the first success will be on the fifth throw? Alternatively, the question could be asked as what is the probability that it takes 4 failures before a success? We will see that each way of asking the question will alter the form of the geometric probability density function slightly, and will change the mean and standard deviation of the geometric PDF. Implicit in the random variable is that the probability of a success is constant, and therefore so is the probability of a failure. For flipping a coin, this is obvious, but in experiments that require skill, such as hitting a baseball or throwing a dart, one might consider that learning during the experiment would alter the probability of a success. The geometric distribution cannot capture learning, thus the historical probability of success is assumed to be constant. The geometric distribution is memoryless. There are very few probability density functions that are what is known as memoryless, and the geometric distribution is the only one with a discrete random variable that is memoryless. As an example, historically Major League Baseball player Jones has a record of hitting the ball for at least an advance to first base with a probability of 0.2. Jones has not had a hit in his last 10 times at bat. What is the probability that Jones will get a hit in his third time at bat? The answer ignores his 10 previous failures. All events prior to the events in current time are irrelevant and thus are considered memoryless. Formally, letter 1d443, letter 1d465 equals letter 1d45b plus letter 1d458, letter 1d465 greater or equal to letter 1d458 plus 1 equals letter 1d443. Letter 1d465 equals letter 1d45b, where k equals number of previous failures. Jones's probability of a hit begins anew each time he comes to bat. This feature of the geometric distribution results in a curious result, drawing parts from a manufacturing process to test for parts that are defective. The geometric distribution begins with a clean slate each time. The tests begin with no consideration of previous test results. More on this when we get to the exponential probability density function. Example 4.17. You play a game of chance that you can either win or lose. There are no other possibilities until you lose. Your probability of losing is p equals 0.57. What is the probability that it takes 5 games until you lose? Let x equals the number of games you play until you lose includes the losing game. Then x takes on the values 1, 2, 3, go on indefinitely. The probability question is p, x equals 5. Try it 4.17. You throw darts at a board until you hit the center area. Your probability of hitting the center area is p equals 0.17. You want to find the probability that it takes 8 throws until you hit the center. What values does x take on? Example 4.18. Problem. A safety engineer feels that 35% of all industrial accidents in the plant are caused by failure of employees to follow instructions. They decide to look at the accident reports, selected randomly and replaced in the pile after reading, until they find one that shows an accident caused by failure of employees to follow instructions. On average, how many reports would the safety engineer expect to look at until they find a report showing an accident caused by employee failure to follow instructions? What is the probability that the safety engineer will have to examine at least 3 reports until they find a report showing an accident caused by employee failure to follow instructions? Let x equals the number of accidents the safety engineer must examine until they find a report showing an accident caused by employee failure to follow instructions. X takes on the values 1, 2, 3. The first question asks you to find the expected value or the mean. The second question asks you to find p, x greater or equal to 3. At least translates to a greater than or equal to symbol. Solution. On average, how many reports would the safety engineer expect to review until they find a report showing an accident caused by something other than failure to follow instructions? This question asks you to find the expected value or the mean. This is the average number of failures from something other than following instructions. The formula for the mean of this geometric distribution is Letter 1 D707 equals letter 1 D438, letter 1 D465 equals 1 letter 1 D45D approximately 2, 8. Note that the mean does not need to be a whole number, although the random variable is discrete and must be a counting number. What is the probability that the safety engineer will have to examine at least 3 reports until they find a report showing an accident caused by employee failure to follow instructions? This question is answered by first defining the random variable. Let x equals the number of accidents the safety engineer must examine until they find a report showing an accident caused by employee failure to follow instructions. X can take on the values 1, 2, 3, 4, infinity. Unlike the binomial distribution with a fixed number of trials, the geometric distribution may have an infinite number of failed trials before a success occurs. This second question asks you to find letter 1 D443, letter 1 D465 greater or equal to 3. At least translates to a greater than or equal to symbol. In a binomial distribution, we saw the solution to questions of more than or less than would be to calculate each probability individually and add from 0 to 3. If the probability of interest is greater than or equal to, the individual probabilities are added from 0 to 3 and then subtracted from 1. Letter 1 D443, letter 1 D465 greater or equal to 3 equals 1 minus letter 1 D443, letter 1 D465 3. Because we cannot add the full range of the geometric distribution random variable because it goes through infinity, an alternative solution is developed. An alternative geometric distribution pair of formulas provides solutions for questions asking for probabilities more than and less than. If the question is, what is the probability it takes more than n events to get first success? Letter 1 D443, letter 1 D465, letter 1 D45B equals 1 minus letter 1 D45D, letter 1 D45B. What is the probability it takes less than n event for success? Letter 1 D443, letter 1 D465, letter 1 D45B equals 1 minus letter 1 D45D, letter 1 D45B. Try 4.18. An instructor feels that 15% of students get below a C on their final exam. They decide to look at final exams, selected randomly and replaced in the pile after reading. Until they find one that shows a grade below a C, we want to know the probability that the instructor will have to examine at least 10 exams. Until they find one with a grade below a C, what is the probability question stated mathematically? Example 4.19. Suppose that you are looking for a student at your college who lives within 5 miles of you. You know that 55% of the 25,000 students do live within 5 miles of you. You randomly contact students from the college until one says they live within 5 miles of you. What is the probability that you need to contact 4 people? This is a geometric problem because you may have a number of failures before you have the one success you desire. Also, the probability of a success stays the same each time you ask a student if they live within 5 miles of you. There is no definite number of trials, number of times you ask a student. Problem A. Let x equals the number of you must ask, one says yes. B. What values does x take on? C. What are P and Q? D. The probability question is P. Solution A. Let x equals the number of students you must ask until one says yes. B. 1, 2, 3, total number of students. CP equals 0.55, Q equals 0.45. DPX equals 4. Try it 4.19. You need to find a store that carries a special printer ink. You know that of the stores that carry printer ink, 10% of them carry the special ink. You randomly call each store until one has the ink you need. What are P and Q? Notation for the geometric. G equals geometric probability distribution function. XGP. Read this as x is a random variable with a geometric distribution. The parameter is p. P equals the probability of a success for each trial. Case I, random variable x is event of first success. In this case, we ask what is the probability that we will have some number x of events of interest to us of failures before a success. The geometric PDF tells us the probability that the first occurrence of success requires x number of failure-independent trials, each with probability 1 minus letter 1 D45D. If the probability of success on each trial is p, then the probability that the xdh trial out of x trials is the first success is letter 1 d443 letter 1 d44b equals letter 1 d465 equals 1 minus letter 1 d45d, letter 1 d465 minus 1 letter 1 d45d. For letter 1 d465 equals 1, 2, 3. Like the binomial distribution, the geometric distribution has the parameters of the mean and standard deviation. The expected value of x, the mean for case I, is letter 1 d707 equals 1 letter 1 d45d. This tells us how many failed trials to expect until we get the first success. This count includes in the count of trials the trial that results in success. The above form of the geometric distribution is used for modeling the number of trials until the first success. The number of trials includes the one that is a success. X equals all trials including the one that is a success. This can be seen in the form of the formula. If x equals number of trials including the success, then we must multiply the probability of failure, 1 minus letter 1 d45d, times the number of failures, that is letter 1 d465 minus 1. The standard deviation of case I of the geometric distribution is letter 1 d70e equals 1 letter 1 d45d, 1 letter 1 d45d minus 1 square. Case II, random variable x is number of failures before a success. By contrast to case I, the following form of the geometric distribution used for modeling number of failures until the first success is letter 1 d443 letter 1 d44b equals letter 1 d465 equals 1 minus letter 1 d45d letter 1 d465 letter 1 d45d. For letter 1 d465 equals 0, 1, 2, 3. In this case, the trial that is the success is not counted as a trial in the formula. X equals number of failures. The expected value, the mean of this distribution, is letter 1 d707 equals 1 minus letter 1 d45d letter 1 d45d. This tells us how many failures to expect before we have a success. In either case, the sequence of probabilities is a geometric sequence. In case II, the standard deviation parameter is letter 1 d70e equals 1 minus letter 1 d45d letter 1 d45d square. Bar graph of probability distribution of the given data. Figure 4.4. Geometric p equals 0.02, common ratio equals r equals 0.98. The y-axis in figure 4.4 contains the probability of x, and the x-axis is the random number components tested. For example, at letter 1 d465 equals 1. The probability it will be found to be defective is 0.0196. With two components tested, the probability the second component is defective is graphed at a probability of 0.0196 at letter 1 d465 equals 2. On the x-axis, for the probability that the third component is defective, we find letter 1 d443, letter 1 d44b equals 3 equals 0, 0.19208. The first two are the same because of rounding in the computations. Notice on figure 4.4 that the probabilities decline by the same step down with each change in the value of x. This increment is called the common ratio. This exists for the geometric probability distribution uniquely. The common ratio, called r, can be calculated by dividing any value by the previous value, e.g., letter 1 d443, letter 1 d465 equals 5 letter 1 d443, letter 1 d465 equals 4 equals 0, 0.184470, 0.18823 equals 0.98. For this set of data, therefore, the common ratio is 0.98. The common ratio then multiplied by any other probability value will provide the next probability value in the sequence. For example, the probability that the sixth component tested is a failure is 0.018078. Check this using the formula from case I. Now we have the letter 1 d443, letter 1 d465 equals 6. Knowing this and the common ratio, we can calculate the letter 1 d443, letter 1 d465 equals 7. By simple multiplication, letter 1 d443, letter 1 d465 equals 7 equals 0, 0.18078, 0, 98 equals 0, 0.17716. The same value we found earlier by using the geometric probability distribution. This common ratio increment is the same ratio between every number and is called a geometric progression, and thus the name for this probability density function. Once the common ratio is calculated, any letter 1d443, letter 1d465 equals letter 1d465, letter 1d44e. One desires to know can be easily found. The number of components that you would expect to test until you find the first defective component is the mean, letter 1d707 equals 50. For this case of defective components, the formula for the mean of the geometric distribution for the random variable defined as number of failures before first success is letter 1d707 equals 1, letter 1d45d equals 10, 0, 2 equals 50. See example 4.2 for an example where the geometric random variable is defined as number of trials until first success. The expected value of this formula for the geometric distribution will be different from this version of the distribution. Case II also has a variance, but this is changed from the case I formula. This formula for the variance is letter 1d443, letter 1d44b equals letter 1d465 equals 1 minus letter 1d45d, letter 1d465 minus 1 letter 1d45d. For letter 1d465 equals 1, 2, 3. The formula for the variance is letter 1d70e2 equals 1 letter 1d45d, 1 letter 1d45d minus 1 equals 10, 0, 2, 10, 0, 2 minus 1 equals 2, 450. The standard deviation is letter 1d70e equals 1 letter 1d45d, 1 letter 1d45d minus 1 square equals 10, 0, 2, 10, 0, 2 minus 1 square equals 49, 5. Example 4.2. Assume that the probability of a defective computer component is 0.02. Components are randomly selected. Find the probability that the first defect is caused by the seventh component tested. How many components do you expect to test until one is found to be defective? Let x equals the number of computer components tested until the first defect is found. X takes on the values 1, 2, 3, where p equals 0.02. Find p x equals 7, p x equals 7 equals 0.0177. Using the T83, 83 plus 84, 84 plus calculator. To find the probability that x equals 7. Enter second distr. Scroll down and select geometry. Press enter. Enter 0.027. Press enter to see the result. P x equals 7 equals 0.0177. To find the probability that x less or equal to 7, follow the same instructions except select geometry as the distribution function. The probability that the seventh component is the first defect is 0.0177. The formula for the variance is sigma 2 equals 1 letter 1d45d, 1 letter 1d45d minus 1 equals 1002, 1002 minus 1 equals 2450. The standard deviation is sigma equals 1 letter 1d45d, 1 letter 1d45d minus 1 square equals 1002, 1002 minus 1 square equals 49.5. Try at 4.2. The probability of a defective steel rod is 0.01. Steel rods are selected at random. Find the probability that the first defect occurs on the ninth steel rod. Use the T83 plus or T84 calculator to find the answer. Example 4.21. Problem. The lifetime risk of developing cancer is about 1 in 67, 1.5%. Let x equals the number of people you ask until one says they have cancer. Then x is a discrete random variable with a geometric distribution. Letter 1d44b tilde letter 1d43a, 167. Or letter 1d44b tilde letter 1d43a, 0, 0, 15. What is the probability of that you ask 10 people before one says they have cancer? What is the probability that you must ask 20 people? Find the I-mean and Roman 2 standard deviation of x. Solution. Letter 1d443, letter 1d465 equals 10 equals letter 1d454, letter 1d452, letter 1d45c, letter 1d45a, letter 1d452, letter 1d461, 0, 0, 15, 10 equals 0, 0, 1, 3, 1. Letter 1 D443, letter 1 D465 equals 20 equals letter 1 D454, letter 1 D452, letter 1 D45C, letter 1 D45A, letter 1 D452, letter 1 D461, 0. 0, 15, 20 equals 0, 0, 1, 1, 3. Mean equals letter 1 D707 equals 1, letter 1 D45D equals 10, 0, 15 equals 66, 67. Standard deviation equals letter 1 D70E equals 1 minus letter 1 D45D, letter 1 D45D, 2 square equals 1 minus 0, 0, 15, 0, 0, 15, 2 square equals 66, 16. Try it 4.21. The literacy rate for a nation measures the proportion of people age 15 and over who can read and write. The literacy rate for women in Afghanistan is 12%. Let X equals the number of Afghani women you ask until one says that she is literate. What is the probability distribution of X? What is the probability that you ask 5 women before one says she is literate? What is the probability that you must ask 10 women? Find the I-mean and Roman 2 standard deviation of X. There are 5 characteristics of a hypergeometric experiment. You take samples from 2 groups. You are concerned with a group of interest, called the first group. You sample without replacement from the combined groups. For example, you want to choose a softball team from a combined group of 11 men and 13 women. The team consists of 10 players. Each pick is not independent since sampling is without replacement. In the softball example, the probability of picking a woman first is 13/24. The probability of picking a man second is 11/23. If a woman was picked first, it is 10/23. If a man was picked first, the probability of the second pick depends on what happened in the first pick. You are not dealing with Bernoulli trials. The outcomes of a hypergeometric experiment fit a hypergeometric probability distribution. The random variable X equals the number of items from the group of interest. Example 4.22. Problem. A candy dish contains 100 jelly beans and 80 gumdrops. 50 candies are picked at random. What is the probability that 35 of the 50 are gumdrops? The 2 groups are jelly beans and gumdrops. Since the probability question asks for the probability of picking gumdrops, the group of interest first group is gumdrops. The size of the group of interest first group is 80. The size of the second group is 100. The size of the sample is 50 jelly beans or gumdrops. Let X equals the number of gumdrops in the sample of 50. X takes on the values X equals 0, 1, 2, 50. What is the probability statement written mathematically? Solution. Px equals 35. Try it 4.22. A bag contains letter tiles. 44 of the tiles are vowels and 56 are consonants. 7 tiles are picked at random. You want to know the probability that 4 of the 7 tiles are vowels. What is the group of interest, the size of the group of interest, and the size of the sample? Example 4.23. Problem. Suppose a shipment of 100 laptops is known to have 10 defective laptops. An inspector randomly chooses 12 for inspection. He is interested in determining the probability that among the 12 laptops at most 2 are defective. The 2 groups are the 90 non-effective laptops and the 10 defective laptops. The group of interest first group is the defective group because the probability question asks for the probability of at most 2 defective laptops. The size of the sample is 12 laptops. They may be non-defective or defective. Let X equals the number of defective laptops in the sample of 12. X takes on the values 0, 1, 2, 10. X may not take on the values 11 or 12. The sample size is 12, but there are only 10 defective laptops. Write the probability statement mathematically. Solution. Px less or equal to 2. Try it 4.23. A gross of eggs contains 144 eggs. A particular gross is known to have 12 cracked eggs. An inspector randomly chooses 15 for inspection. She wants to know the probability that among the 15 at most 3 are cracked. What is X and what values does it take on? Example 4.24. You are president of an on-campus special events organization. You need a committee of 7 students to plan a special birthday party for the president of the college. Your organization consists of 18 women and 15 men. You are interested in the number of men on your committee. If the members of the committee are randomly selected, what is the probability that your committee has more than 4 men? This is a hypergeometric problem because you are choosing your committee from 2 groups, men and women. Problem. A. Are you choosing with or without replacement? B. What is the group of interest? C. How many are in the group of interest? D. How many are in the other group? E. Let X equals on the committee. What values does X take on? F. The probability question is P. Solution: A. Without. B. The men. C. 15 men. D. 18 women. E. Let X equals the number of men on the committee. X equals 0, 1, 2, 7. FPX4. Try it 4.24. A pallet has 200 milk cartons. Of the 200 cartons, it is known that 10 of them have leaked and cannot be sold. A stock clerk randomly chooses 18 for inspection. He wants to know the probability that among the 18, no more than 2 are leaking. Give 5 reasons why this is a hypergeometric problem. Notation for the hypergeometric. H equals hypergeometric probability distribution function. XHRBN. Read this as X is a random variable with a hypergeometric distribution. The parameters are R, B, and N. R equals the size of the group of interest, first group, B equals the size of the second group, N equals the size of the chosen sample. Example 4.25. A school site committee is to be chosen randomly from 6 men and 5 women. If the committee consists of 4 members chosen randomly, what is the probability that 2 of them are men? How many men do you expect to be on the committee? Let X equals the number of men on the committee of 4. The men are the group of interest, first group. X takes on the values 0, 1, 2, 3, 4, where R equals 6, B equals 5, and N equals 4. XH 6, 5, 4. Find P X equals 2. P X equals 2 equals 0.4545 calculator or computer. Note: currently, the T83 Plus and T84 do not have hypergeometric probability functions. There are a number of computer packages, including Microsoft Excel, that do. The probability that there are 2 men on the committee is about 0.45. The graph of XH654 is. This graph shows a hypergeometric probability distribution. It has 5 bars that are slightly normally distributed. The x-axis shows values from 0 to 4 in increments of 1, representing the number of men on the 4-person committee. The y-axis ranges from 0 to 0.5 in increments of 0.1. Figure 4.5. The y-axis contains the probability of x, where x equals the number of men on the committee. You would expect m equals 2.18, about 2 men on the committee. The formula for the mean is letter 1D707 equals letter 1D45B, letter 1D45F, letter 1D45F, plus letter 1D44F equals 4, 6, 6 plus 5 equals 2, 18. Try it 4.25. An intramural basketball team is to be chosen randomly from 15 boys and 12 girls. The team has 10 slots. You want to know the probability that 8 of the players will be boys. What is the group of interest and the sample? There are 2 main characteristics of a Poisson experiment. The Poisson probability distribution gives the probability of a number of events occurring in a fixed interval of time or space if these events happen with a known average rate and independently of the time since the last event. For example, a book editor might be interested in the number of words spelled incorrectly in a particular book. It might be that, on the average, there are 5 words spelled incorrectly in 100 pages. The interval is the 100 pages. The Poisson distribution may be used to approximate the binomial if the probability of success is small, such as 0.01, and the number of trials is large, such as 1,000. You will verify the relationship in the homework exercises. N is the number of trials, and P is the probability of a success. The random variable x equals the number of occurrences in the interval of interest. Example 4.26. The average number of loaves of bread put on a shelf in a bakery in a half-hour period is 12. Of interest is the number of loaves of bread put on the shelf in 5 minutes. The time interval of interest is 5 minutes. What is the probability that the number of loaves selected randomly put on the shelf in 5 minutes is 3? Let x equals the number of loaves of bread put on the shelf in 5 minutes. If the average number of loaves put on the shelf in 30 minutes, half hour, is 12, then the average number of loaves put on the shelf in 5 minutes is 530. 12 equals 2 loaves of bread. The probability question asks you to find P x equals 3. Try it 4.26. The average number of fish caught in an hour is 8. of interest is the number of fish caught in 15 minutes. The time interval of interest is 15 minutes. What is the average number of fish caught in 15 minutes? Example 4, 27. Problem. The bank expects to receive 6 bad checks per day on average. What is the probability of the bank getting fewer than 5 bad checks on any given day? Of interest is the number of checks the bank receives in one day, so the time interval of interest is 1 day. Let x equals the number of bad checks the bank receives in one day. If the bank expects to receive 6 bad checks per day, then the average is 6 checks per day. Write a mathematical statement for the probability question. Solution. px5. Try it for 27. An electronics store expects to have 10 returns per day on average. The manager wants to know the probability of the store getting fewer than 8 returns on any given day. State the probability question mathematically. Example 428. You notice that a news reporter says on average 2 times per broadcast. What is the probability that the news reporter says more than 2 times per broadcast? This is a Poisson problem because you are interested in knowing the number of times the news reporter says during a broadcast. Problem. A. What is the interval of interest? B. What is the average number of times the news reporter says during one broadcast? C. Let x equals. What values does x take on? D. The probability question is P. Solution. A. 1 broadcast. B. 2. C. Let x equals the number of times the news reporter says during one broadcast. X equals 0, 1, 2, 3, dp x2. Try it for 28. An emergency room at a particular hospital gets an average of 5 patients per hour. A doctor wants to know the probability that the ER gets more than 5 patients per hour. Give the reason why this would be a Poisson distribution. Notation for the Poisson. P equals Poisson probability distribution function. Xp mu. Read this as x is a random variable with a Poisson distribution. The parameter is mu or lambda. Mu or lambda equals the mean for the interval of interest. The standard deviation of the Poisson distribution with mean micro is sigma equals square mu. Example 4. 29. Lee receives about 6 telephone calls between 8 a.m. and 10 a.m. What is the probability that Lee receives more than 1 call in the next 15 minutes? Let x equals the number of calls Lee receives in 15 minutes. The interval of interest is 15 minutes or 14 hours. X equals 0, 1, 2, 3. If Lee receives on the average 6 telephone calls in 2 hours, and there are 8 15-minute intervals in 2 hours, then Lee receives 18. 6 equals 0, 75 calls in 15 minutes on average. So mu equals 0, 75 for this problem. Using the T83, 83 plus 84, 84 plus calculator. Press 1 and then press second DISDR, arrow down to Poisson, press enter, enter. 751, the result is px1 equals 0, 1734. Note. The T calculators use lambda for the mean. The Poisson distribution is discrete, and thus 1 includes all whole numbers through infinity. The solution is to subtract the probability less than 1, thus 1 minus letter 1 d443, letter 1 d465 equals 0, plus letter 1 d443, letter 1 d465 equals 1. Letter 1 d443, letter 1 d465 equals letter 1 d707, letter 1 d465, letter 1 d452, minus letter 1 d707, letter 1 d465. Letter 1 d443, letter 1 d465, 1 equals 1 minus letter 1 d443, letter 1 d465 less or equal to 1, equals 1 minus letter 1 d443, letter 1 d465 equals 0, plus letter 1 d443, letter 1 d465 equals 1, equals 1 minus 0. 750 letter 1 d452 minus 0. 750 plus 0, 751, letter 1 d452 minus 0, 751, equals 1 minus 1, 0. 4724, 1 plus 0, 75, 0, 4724, 1, equals 1 minus 0, 4724 plus 0, 3543 equals 0. 1733. Histogram of probability density function of the given data, figure 4.6. The y-axis in figure 4 6 contains the probability of x, where x equals the number of calls in 15 minutes. Try it for 29. A customer service center receives about 10 emails every half hour. What is the probability that the customer service center receives more than 4 emails in the next 6 minutes? Example 4. 30. According to Baden, an email management company, an email user gets, on average, 147 emails per day. Let x equals the number of emails an email user receives per day. The discrete random variable x takes on the values x equals 0, 1, 2. The random variable x has a Poisson distribution, x p 147. The mean is 147 emails. Problem: what is the probability that an email user receives exactly 160 emails per day? What is the probability that an email user receives at most 160 emails per day? What is the standard deviation? Solution: Px equals 160 equals Poisson 147 160 approximately 0. 180. Px less or equal to 160 equals Poisson 147 160 approximately 0. 8666. Standard deviation equals letter 1d70e equals letter 1d707 square equals 147 square approximately 12. 1244. Try it for 30. According to a recent poll by the Pew Internet Project, people between the ages of 14 and 17 send an average of 187 text messages each day. Let x equals the number of texts that a girl aged 14 to 17 sends per day. The discrete random variable x takes on the values x equals 0, 1, 2. The random variable x has a Poisson distribution. X tilde p 187. The mean is 187 text messages. What is the probability that a person sends exactly 175 texts per day? What is the probability that a person sends at most 150 texts per day? What is the standard deviation? Example 431. Text message users receive or send an average of 41.5 text messages per day. Problem: how many text messages does a text message user receive or send per hour? What is the probability that a text message user receives or sends 2 messages per hour? What is the probability that a text message user receives or sends more than 2 messages per hour? Solution: let x equals the number of texts that a user sends or receives in 1 hour. The average number of texts received per hour is 41,524. Approximately 172.92. X p 1, 72.92, so p x equals 2 equals Poisson 1. 72.92 2 approximately 0, 26.53. Px2 equals 1, px less or equal to 2 equals 1, Poisson 1. 72.92 2 approximately 1, 0. 74.95 equals 0, 25.05. Try it for 31. Atlanta's Hartsfield-Jackson International Airport is the busiest airport in the world. On average, there are 2,700 arrivals and departures each day. How many airplanes arrive and depart the airport per hour? What is the probability that there are exactly 100 arrivals and departures in 1 hour? What is the probability that there are at most 100 arrivals and departures in 1 hour? Example 4.32. Problem: on a certain day in May starting at 4:30 p.m., the probability of low seismic activity for the next 48 hours in Alaska was reported as about 1–2%. Use this information for the next 200 days to find the probability that there will be low seismic activity in 10 of the next 200 days. Use both the binomial and Poisson distributions to calculate the probabilities. Are they close? Solution: let x equals the number of days with low seismic activity, using the binomial distribution. Px equals 10 equals binomf 200, 102, 10 approximately 0.39. Using the Poisson distribution. Calculate mu equals np equals 200, 0, 102 approximately 2, 4. Px equals 10 equals Poisson 2, 4, 10 approximately 0. 45. We expect the approximation to be good because n is large, greater than 20, and p is small, less than 0. 5. The results are close. Both probabilities reported are almost 0. Try it for 32. On a certain day in May starting at 4:30 30 p.m., the probability of moderate seismic activity for the next 48 hours in the Kuril Islands off the coast of Japan was reported at about 1.43%. Use this information for the next 100 days to find the probability that there will be low seismic activity in 5 of the next 100 days. Use both the binomial and Poisson distributions to calculate the probabilities. Are they close? Stats Lab. Discrete distribution, playing card experiment. Class time names. Student learning outcomes. The student will compare empirical data and a theoretical distribution to determine if an everyday experiment fits a discrete distribution. The student will compare technology-generated simulation and a theoretical distribution. The student will demonstrate an understanding of long-term probabilities. Supplies: 1 full deck of playing cards, 1 programming calculator. Procedure: the experimental procedure for empirical data is to pick 1 card from a deck of shuffled cards. The theoretical probability of picking a diamond from a deck is shuffle a deck of cards, pick 1 card from it, record whether it was a diamond or not a diamond, put the card back and reshuffle. Do this a total of 10 times. Record the number of diamonds picked. Let x equals number of diamonds, theoretically x tilde b. Organize the data. Record the number of diamonds picked for your class with playing cards in table 416. Then calculate the relative frequency. X frequency, relative frequency. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Table 416. Calculate the following. Letter 1d465 equals S equals. Construct a histogram of the empirical data. This is a blank graph template. The x-axis is labeled number of diamonds. The y-axis is labeled relative frequency. Figure 4. 7. Theoretical distribution. Build the theoretical PDF chart based on the distribution in the procedure section. XPX. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Table 4. 17. Calculate the following. Mu equals. Sigma equals. Construct a histogram of the theoretical distribution. This is a blank graph template. The x-axis is labeled number of diamonds. The y-axis is labeled probability. Figure 4.8. Using the data. Note: RF equals relative frequency. Use the table from the theoretical distribution section to calculate the following answers. Round your answers to 4 decimal places. Px equals 3 equals. P1x4 equals. Px greater or equal to 8 equals. Use the data from the Organize the Data section to calculate the following answers. Round your answers to 4 decimal places. RF x equals 3 equals. RF 1x4 equals. RF x greater or equal to 8 equals. Discussion questions. For questions 1 and 2, think about the shapes of the 2 graphs, the probabilities, the relative frequencies, the means, and the standard deviations. Knowing that data vary, describe 3 similarities between the graphs and distributions of the theoretical, empirical, and simulation distributions. Use complete sentences. Describe the 3 most significant differences between the graphs or distributions of the theoretical, empirical, and simulation distributions. Using your answers from questions 1 and 2, does it appear that the 2 sets of data fit the theoretical distribution? In complete sentences, explain why or why not. Suppose that the experiment had been repeated 500 times. Would you expect table 416 or table 417 to change, and how would it change? Why? Why wouldn't the other table S change? Stats Lab. Discrete distribution, dice experiment using 3 regular dice. Class time names, student learning outcomes. The student will compare empirical data and a theoretical distribution to determine if a dice experiment game fits a discrete distribution. The student will demonstrate an understanding of long-term probabilities. Supplies: 3 regular 6-sided dice. Procedure: round answers to relative frequency and probability problems to 4 decimal places. The experimental procedure is to bet on a specific number appearing on the dice. Then, roll 3 dice and count the number of matches. The number of matches will decide your profit. What is the theoretical probability of 1 die matching the specific number? Choose 1 number to place a bet on. Roll the 3 dice. Count the number of matches. Let x equals number of matches. Theoretically x tilde b. Let y equals profit per game. Organize the data. In table 418, fill in the y value that corresponds to each x value. Next, record the number of matches picked for your class. Then calculate the relative frequency. Complete the table, XY frequency relative frequency. 0, 1, 2, 3. Table 418. Calculate the following. Letter 1D465 equals SX equals letter 1D466 equals Z equals. Explain what letter 1D465 represents. Explain what letter 1D466 represents based upon the experiment. What was the average profit per game? Did this represent an average win or loss per game? How do you know? Answer in complete sentences. Construct a histogram of the empirical data. This is a blank graph template. The x-axis is labeled number of matches. The y-axis is labeled relative frequency. Figure 4.9. Theoretical distribution. Build the theoretical PDF chart for x and y based on the distribution from the procedure section. XYPX equals PY. 0, 1, 2, 3. Table 419. Calculate the following. Mux equals. Sigmix equals. Mux equals. Explain what mux represents. Explain what mui represents. Based upon theory, what was the expected profit per game? Did the expected profit represent an average win or loss per game? How do you know? Answer in complete sentences. Construct a histogram of the theoretical distribution. This is a blank graph template. The x-axis is labeled number of diamonds. The y-axis is labeled probability. Figure 410. Use the data. Note, RF equals relative frequency. Use the data from the theoretical distribution section to calculate the following answers. Round your answers to 4 decimal places. Px equals 3 equals. P0x3 equals. Px greater or equal to 2 equals. Use the data from the Organize the Data section to calculate the following answers. Round your answers to 4 decimal places. RF x equals 3 equals. RF 0x3 equals. RF x greater or equal to 2 equals. Discussion question. For questions 1 and 2, consider the graphs, the probabilities, the relative frequencies, the means, and the standard deviations. Knowing that data vary, describe 3 similarities between the graphs and distributions of the theoretical and empirical distributions. Use complete sentences. Describe the 3 most significant differences between the graphs or distributions of the theoretical and empirical distributions. Thinking about your answers to questions 1 and 2, does it appear that the data fit the theoretical distribution? In complete sentences, explain why or why not. Suppose that the experiment had been repeated 500 times. Would you expect Table 418 or Table 419 to change, and how would it change? Why wouldn't the other table change?